We've got a cubic function. We're told that 2 minus 3i is a root of f of z equals 0. Write down the other root. So this is just the complex conjugate, 2 plus 3i. Hence solve completely, f of z equals 0. Okay, two ways to do this. First up, I'm going to use roots and polynomials. So we know that the sum of the roots is going to equal minus b over a. Right, and actually let me just write it in the correct form because there's no z squared term here. So z cubed plus 0z squared plus az plus 52. So this here is a, like 1 is a, then b is 0, c is a, so maybe I should just put little inverted commas around that one, and d is 52. So the sum of the roots is minus b over a. In this case, it's going to be 0. And actually, I think we can use that now. So we've got the 2 plus 3i plus 2 minus 3i plus my third root gamma must equal 0. That means gamma is going to equal minus 4. And then we're asked to determine the value of a. Well, let's carry on with our roots of polynomial idea. So the sum of the pairs of the roots is then c over a, which in this case is going to be, this is inverted commas again. It's a bit confusing when they call that a, because a is always the leading coefficient. So here we're going to actually get a. Right, so now I just need to go with 2 plus 3i multiplied by 2 minus 3i plus 2 plus 3i times minus 4 plus 2 minus 3i times minus 4. And that's going to equal a. So let's multiply. We're going to get 4 minus 6i plus 6i. We're going to get minus 9i squared. So that's plus 9. And over here, I've got minus 8 minus 12i. Then minus 8 plus 12i. And that's going to equal a. They cancel. 13 minus 16 is equal to a. So a is minus 3. So that's my recommended way of doing this question. You could also have used the product of the roots, which is then equal to minus d over a, which would have been minus 52. And then if you'd subbed in for alpha beta, you can see we got 13 from here. 13 gamma is minus 52, and gamma would again have been minus 4 from this. Just an alternative instead of using the sum of the roots, but the sum of the roots is a little bit quicker. Other method you could have used is just to multiply the brackets out. So go with z minus 2 plus 3i times z minus 2 minus 3i to get the quadratic, and then we're going to figure out what other term there is to get this. So this would give z squared, and then we'd get plus this times this. Well, that's going to be minus, plus 13. We've already actually shown that. And then we'd get minus 2z, and then another minus 2z. The i's would cancel, we get minus 4z. Let me just write it as z squared minus 4z plus 13. What we could then do is write that down. Actually, do you know what? I'm just going to kind of be a bit cheeky and put it here. Okay, and then I need another factor such that I'm going to get this. And I can see that I need a 4 here to get the 52. So it's got to be z plus 4. Now we could just double check and see that we don't get a z squared term. So we'd get 4z squared minus 4z squared. So you can see we don't. And then if you wanted to get the a term, then it would come from doing 13 times z and minus 16z, which would give minus 3z. So it's just an alternative way of, once you've got that complex root, of finding the other roots by using factors instead and getting this, and then multiplying through appropriately just to check that you get no z squared term, finding out what the z term is, and that gives a. Finally, we're asked to show all the roots of the equation on an Argand diagram. It's just a sketch. So we've got the real axis and the imaginary axis. Okay, and then we had -4. Oh, sorry, it should have been here. So -4. And then 2 plus 3i. And 2 minus 3i. That'll be fine. There's different ways of representing an Argand diagram. I normally connect them up just to show that like, the complex number has a length and everything, but this is not vital. And I think just best practice would be to write on what it is. 2 plus 3i. Well done.